Hello everyone. Today we're going to be talking about Unit 3. The topic is going to be making inferences about population parameters. As usual, I'm not able to, cover the entire chapters here because the amount of time that it would take to do something like that would be prohibitive, but I am going to touch on a couple of basic ideas on what this topic is about, and then I'll give you a couple of examples on hypothesis testing using Excel. Now, the topic title sounds kind of fancy. It says making inferences about population parameters. The basic idea is this. Let's say you want to know if a particular idea is true. Maybe you are interested in whether male runners in United States run faster than female runners in United States. Okay? Or maybe you want to know if I don't know, boys cry more than girls. Or maybe you want to know something else. If you want, if Ford Escort, well, that's an old car. What's the new car? Mm, I'm drawing a blank on the new car models. Let's say, let's talk about SUVs. Let's say you want to know in real life, not in testing, but in real life, if a BMW X5 gets better gas mileage on the road compared to Lexus 350. Okay, how about that? Anyway, so suppose you have these questions in your mind. Now, the only way to get an answer for these things for sure is to test everybody and everything. Okay, so if you want to know the answer to this question for sure, if male runners in the United States run faster than female runners in the United States, to know the answer to this for certain, you would have to time every single runner in the United States, divide them into male and female categories, and then compare their times. If you did that, then you would actually have the correct answer to that question, because the question is about all of them. Okay, so the question is about the population, the entire population. Now, in many situations, like in those examples I gave above, and in many other situations in real life, testing the entire population is not practical, and it may not even be possible at all. Okay, so you may not be able to go out and actually find every single BMW X5 and every single Lexus 350 out on the road so you can test them. So even if you had the money and the motivation to do that, you may not be able to do that. You're not going to be able to time every single runner, male or female, in America. So instead of testing the population and giving an answer for the population, what we do is take some samples from that population and base our answer on that sample. Okay, so maybe we find a group of 100 runners, 50 male, 50 female, and we time them, and then we make some assumptions based on their times, and then we make a conclusion and we say we think based on our samples here the population of males versus females is like this. Now the problem with that is that if you're going to take a sample from a population, you are hoping basically that the sample you have taken is representative of the entire population, but that is never guaranteed. Okay, so if you look at a sample group of runners, male and female, it is entirely possible that the sample that you have picked, the sample runners male that you have picked, run faster than the average male runners overall, or they might run slower. Okay, so we are not entirely sure. So we cannot just pick a sample of 100 runners, 50 males, 50 females, compare their averages, and if the average of one group is better than the average of the other group, then conclude that the group with the better average is actually running faster in terms of the population. Okay, so if you take 50 male runners and 50 female runners and you time them, and the female runners end up being better on average by about, let's say, 2 seconds over 100 meters, you cannot just say, well, the average of the female runners was better than the average of the male runners, so I'm going to conclude that females overall run better. You cannot make that conclusion because it is entirely possible that the sample that you have picked is not representative of the two genders. And if you had picked a better sample, or if you had picked another group of runners, that time might come in differently. Okay, so in order to make what we call a statistically significant conclusion, the difference between the two groups will have to be significantly different than each other. If there is a significant difference between the averages of the two groups, then you can make a suggestion that the population of the males versus the females is like this. Okay, because if the difference is significant enough between the averages of the two samples, then you can conclude that even if I took a completely different sample, the averages might change a little bit, but the averages are not going to change so much that this difference between the two groups is going to be reversed. Okay, so we cannot just look at the averages of the two groups and make a conclusion based on that. We want to see a significant difference between the averages of the two groups before we can say confidently that with any sample that I pick, the difference is going to be pretty much like this. Okay, now the big question that follows from this, of course, is, well, how big a difference do you need to see between the two groups before you can say confidently that there is a difference here? Okay, and that comes through our computations with the t-tables and the z-tables and hypothesis testing that you read in our chapter. So I'm going to give you a couple of examples and we'll talk about it some more. Now I'm going to do this through Excel's data analysis tools. Alright, in Unit 3 assignment, a couple of the problems are supposed to be done on paper. And only the last problem is really supposed to be done using the methodology that I'm going to show you here. Okay, so do not try to apply this methodology to every single hypothesis testing problem you're going to see, but it's difficult for me to show you how to do things on paper when I'm doing a screen recording, and we're going to do this in Excel because it also accelerates the time it takes. Okay, so let's take a look at this. I have here a data set. Okay, I have from a company a selection of 69 employees, 69 male employees and 69 female employees, and these are the salaries that each one is making. $39,000 per year, $33,000 per year, $30,000 per year, and so on. Okay, and I want to know if there is a difference between the average female salary and the average male salary. And here is how we do this. I'm going to go to data analysis, and I am going to pick t-test 2 sample assuming unequal variances. Okay, there are a few different options you have here. They all refer to different types of tests. For example, the paired 2 sample for means is for before and after type of comparisons. So if you have a group of people who have been performing in a particular way, you record their performance and then you do something, maybe implement an incentive program or hire a new boss or something, and then you record their performance after the change. In a situation like that, you would have a paired 2 sample for means test because you have a single group who are being compared before and after they are paired. Okay, in our situation I'm going to use the 2 sample assuming unequal variances. The actual running of the tool is actually pretty simple. Variable 1 range is the female salary range all the way down to 69. Variable 2 range is the male salary range. So the 2 columns that I'm going to be comparing. Okay, so A1 through A69, B1 through B69. I click on the box that says labels because at the top of my data set over here, you can see that I have labels. If you forget to do this, and if you hit OK, you'll get an error. It says input range contains non-numeric data. It contains text. Okay, so you say OK, and then you click on labels because the first row includes text. And then I could get the new output to a new worksheet ply, but I want this output to come in here. Okay, so I'm just going to do that. And we will look at the result. Okay, Excel calculates everything almost immediately and gives me some numbers. So let's take a look at this and see what's going on. I zoomed in just a little bit. Here are the averages. The female salary average was $33,000. The male salary average was $45,000. And if you read your book, you will see certain things that are familiar to you. The t-value, t-stat, the cutoff values, the t-critical one tail and t-critical two tail. Okay, now by just looking at this, you might say, well, this looks like a significant difference between the averages. Even without looking down here, you might say, I'm going to make a conclusion that there is indeed a significant difference between the two groups. And you might be right. So let's take a look at the numbers down here. There are multiple ways to actually make the conclusion based on the numbers that you see here. Before I tell you about those, I'm going to explain what this number means. The 1.2038 e minus 0.8, this is the scientific notation. It basically means you have a decimal point and then you have 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, before you actually get that number, 1, 2, 0, 3, 8, 1. Okay? If Excel tries to put that number in here, sorry about that, I put down one too many zeros. There will be too many zeros for you to comfortably see all the important digits, so instead of doing that, it basically says, I'm going to write it somewhat differently. And I'm going to write it like it was 1.20, but it actually has 8 zeros in front of it. Okay, so counting from here, 1, 2, 3, 4, 5, 6, 7, 8. Alright, there we go. So the e minus 0.8 only means that there are that many zeros in front of it and that this is a very, very small number. If you want Excel to actually put down the zeros, you can actually force it. You can say, I want to have a number there, and you would have to increase the decimal points before you actually see the number. Okay, there you go. So this is the e minus 0.8 is just a shorthand way of writing a very, very small number. Okay, there are a couple of different ways of deciding the result of the test. One of them is looking at the t-stat and comparing it with the cutoff values where you have the critical one tail and the critical two tails. But what I prefer in general is to look at the p-values. And the basic idea here is this. I'll actually write it down. If the p-value is less than 0.05, then you can reject the null hypothesis with 95% confidence. Alright, if the p-value is less than 0.05, then you can reject the null hypothesis with 95% confidence. The 95% confidence comes from the 0.05. Okay, it's 1 minus 0.05, that's how confident you are. If the p-value is less than 0.01, for example, then you can reject the null hypothesis with 99% confidence, and it goes on like that. Okay, so if the p-value is less than 0.05, you can reject the null hypothesis with 95% confidence. What is the null hypothesis? If you read the book, you would know that the null hypothesis in situations like this is that there is no difference in the means between the two groups. Okay, the null hypothesis, let me write that down here too. Null hypothesis would say the mean for the female group is equal to the mean for the male group. And you could also write this as the mean for the female group minus the mean for the male group is equal to 0. There is no difference between them. Okay, so that's the null hypothesis. So let's take a look at our P2 tail, since we are saying if there is any difference, higher or lower, between the two groups. This number is what? Is this number bigger or smaller than 0.05? Well, I just explained about the exponential minus 0.8 issue. So this number is actually, let me show it to you in real numbers, increase the decimal points. This number is actually this. This is very, very small. It is definitely smaller than 0.05. So what we are going to do is reject the null hypothesis that the mean for the female group is equal to the mean for the male group. Okay, so we are going to conclude that the averages of the two groups is not actually the same. Alright, so you might have said, well, I don't need all that fancy t-stats and the p-values and the t-tables and all that stuff. This is 33,000, this is 45,000. That looks pretty different to me. Why are we even bothering with this? Okay, so I'm going to show you another example where the difference is not quite so clear. Here is another data set. This is from a school district of students, their writing and reading and math and citizenship and science scores. Okay, so let's just take a look at writing and reading. I'm going to delete these other columns. I'm not interested in those. So over these school districts, I am interested in finding out if there is a difference between their writing scores and the reading scores. Okay, are these students reading as well as they are writing, and are they writing as well as they are reading? Okay, so let's take a look. I'm going to do the same thing. Data analysis, t-sample, excuse me, I keep saying t-sample, 2 sample, assuming unequal variances. Variable 1 range is going to be the writing group. The variable 2 range is going to be the reading group. Okay, I have labels at the very top, and I want the output to appear right here so we can take a look. So let's take a look at this. Immediate answers from Excel. Here's what we are looking at. Let me zoom in a little bit. Is that too much? Here we go. Let's look at the averages. The writing average is almost 85. The reading average is about 81.3. Now, if you are going by only the averages, you might look at this and you might say, well, there is clearly a difference between the means. Okay, they're not like 81 and 81, they're not like 85 and 85, they are 85 and 81.3. Okay, you might say that seems like a different average. One of them is higher than the other. There is no dispute that writing average is higher than the reading average. But once again, we are looking at samples here. And the samples, different samples might give us slightly different results. So is this difference between the two groups significant enough for us to say conclusively that yes, there is a difference between these two groups? Or are they too close to each other for us to say, well, maybe if I took a bunch of different samples, these numbers might change, and if they change, they might actually reverse the outcome that I'm seeing here. So is that difference great enough for us to conclude confidently that there is a significant difference here? Well, let's look at our numbers. Once again, t-stat, the cutoff values are here, but we are going to look at the p-values. Remember our rule from the previous worksheet. If the I'm writing in the wrong place. Let me copy and paste this over here. Control copy. Give me a second. Higher education. Our rule was if the p-value is less than 0.05, then you can reject the null hypothesis with 95% confidence. The null hypothesis here would be that the mean for writing in this school district would be equal to the mean for reading scores in this district. Okay, the p-value here says 0.16. Is that great? Is that less than 0.05? No, it's not. So we cannot reject the null hypothesis, and we have to conclude that we cannot find a significant enough difference between the writing group and the reading group. Okay, although, now here's the most important thing again. Although, just looking at the averages, the average of writing is greater than the average of reading, we cannot statistically significantly conclude with any sort of confidence, we cannot conclude that there is actually a significant difference between the two groups. Okay, so the overall point here is you cannot just take the averages of the two groups, compare them, and make a conclusion. Okay, it is very, very unlikely that you would come up with the exact same average anyway, so one of them would end up being higher than the other regardless, in most situations. The question is, are they significantly different than each other? And of course, how are we going to decide what exactly constitutes significant difference? The p-value is the one that tells us that. Or we can go by the t-values, the t-stat and the cutoff values for the t-criticals, and that's the way that you would calculate these by hand when you do problems, I can't remember, 1, 2, and maybe 3 in the assignment. Okay, but the overall point that I want you guys to take away from this is that when somebody says if there is a difference between the average of one thing versus the average of the other thing, you cannot just actually calculate the average, compare the two numbers that you see here, and say, well, I can see it very clearly, there is a difference between the averages. Okay, that is not a good enough way for us to make a confident answer, confident conclusion. You actually have to go through the statistical analysis, which will tell you if the difference between them is significant enough for you to conclude that taking different samples is not actually going to result in a different outcome. Okay, so hopefully what you have seen here is going to help you with the assignment and this week's topic. I do see a lot of people stumbling when it comes to the last problem, which requires you to use Excel. So hopefully what you saw here is going to help you understand what you need to do there. This also is going to come up in the final project. I think question 3 in the final project has you doing a hypothesis test. So remember to come back to this lecture perhaps when you're tackling the final project as well. Alright, so this was not too bad, 23 minutes. I hope you enjoyed what you saw. If you have any questions, as always, please email me and I'll be more than happy to clear up any confusions. Alright, thank you very much.